Good afternoon, everybody. Mm, uh, this is Kabir. I'm a regional soil health specialist for California, working from Davis, California, and also working for Nevada, Pacific Island areas, and also acting as an Arizona regional soil health specialist. So I would like to present the ecological management. So this module is the ecological management, and I'm going to talk about, this is the outline summarizing how do soil health management system impact nutrient management. That includes also mineralization, immobilization. Also, we are looking at the carbon nitrogen ratio, and we're also looking at the nitrogen and phosphorus cycling, because these are the most important major nutrients and also causing major problem for ag land. Talk about also carbon and organic matter management, the pools and also fluxes. And we'll also touch a little bit on water management and water cycling. Pest management part of this ecological management is going to be insect, disease, and weed management. So let's start with the nutrient management and mineralization, immobilization, CN ratio, nitrogen, and phosphorus cycling. Dominant farming system in annual crops in the nation, in the USA, are performing poor soil health practices. So what we do, we do a lot of tillage, we are losing a lot of organic matter from the soil. So, and soil became, poor. So what do? We adding more and more fertilizer. So here's the dominant nutrient management strategy. Most of the croplands or majority of the croplands are doing this dominant nutrient management strategy. We apply a lot of nutrients, and soil cannot uh, actually uh, hold those excessive nutrients. So what they do, look at here, the width of the, let me see, arrow is showing that uh, and how much actually you are applying. And once we are applying this to increase meet the goals, uh, and soil also use the fertilizer, that soil cannot hold those nutrients, so it became leaky. So it goes, this nutrient, nitrogen and phosphorus, let's say, is going to the soil solution, and part of it taken up by the plant, but and nitrogen, especially, actually some of them are leaching, and also part of it actually running off. And also we are losing in the gaseous format. Some of the phosphorus is fixed in the soil, because soil phosphorus is really reactive to the soil, and a little bit of phosphorus is coming to the soil solution. And in this case, phosphorus also lost with the soil erosion. And plant and residues are much lower in this case, because they are not adding up any organic matter or anything in there. So the depleting also the soil organic matter and also disappearing soil habitats. So here you can see the system is in annual crop about 4 to 8 months is remaining fallow. So there is no food for the soil biology or life. And if it is in a perennial system, in an orchard or vineyard, then also if you are leaving the land bare ground, also it also hampers soil habitats. Does it also people knows about the 4R strategy? I'm sure you knows about this, right? The 4R strategy actually what? Those are right source, right rate, right time, and right placement of nutrient. So these are the 4 strategy what they actually did to increase the efficiency of nutrient in the soil. So in this case, they would do side dressing, binding, fertigation, split application, side dressing as well. And also they would like nitrogen for especially nitrogen, they use the nitrogen inhibitors. That increase the efficiency, but do not eliminate nutrient losses. So you can see the arrow is a little bit narrower than the dominant nutrient management paradigm. So here, nitrogen, phosphorus go to the soil solution. More efficiently use nitrogen, phosphorus, and nitrogen is still leaching and running off, and some of it actually goes to the air. Phosphorus still fixed by the soil because of the system, and less phosphorus is coming to the soil solution. It has the same system as dominant nutrient management paradigm. Is plant and residues is little bit is coming to the soil, and depleting soil organic matter and soil life. So in these two systems, soil organic matter actually lasts maybe 30, 40 years. We lost about 60% of soil organic matter. So it's remained the same situation, fallow field for the annual and perennial crop. So is in last 40 years, actually, nitrogen phosphorus efficiency only 50%. So where the other 50% goes, it actually goes to the environment, polluting soil and water and the air.
If you want to put a cash crop on that field, and we've done this, all of a sudden you're growing your own fertilizer through nitrogen from the organic matter. And maybe we've done it to where we haven't put any commercial fertilizer on and had the same yield. We run them side by side. But even if you can't do that every year, maybe you can do a fourth, maybe you can do a half.
So this is a chemical paradigm. You know, they are using the simple cropping systems and maximize nutrient concentration in space and time, and also shows that annual nitrogen phosphorus application is much higher than harvested export by the crops. So in Iowa, here's an example you see. They quantify, the effectiveness of 4R strategy. State of Iowa actually is planning to reduce nutrient loss in the Gulf of Mexico. So the goal is 45% reduction of nitrogen loading to the stream. So 4R strategy they use, and this nitrogen loading they can reduce by 11%. So to get the target, to reduce the 45% reduction of nitrogen loading, they need to increase cover crops from 600,000 acres to 12 million acres. And also they need to increase the wetland from 81 to 7,000. So what does it mean? So we have to go beyond 4R strategy. That means soil health practices. The question is, this dominant and 4R strategy, nutrient management, does it follow the soil health principles? No, it doesn't. Here you can see it doesn't minimize disturbance. It doesn't minimize soil cover, biodiversity, or living roots. So it is here we can come the holistic approach to nutrient management.
Back when we were in a conventional system, we would put 200 to 220 pounds of nitrogen on a field for corn. Now then, we're going out there and we're coming out with 165 pounds of nitrogen and still raising the yields comparable to the guys that are putting on 220 in a conventional system and letting that nitrogen go right down the creek. We don't like that.
Holistic approach of nutrient managing achieve the high yields, but minimize chemical fertilizer use and reduce environmental pollution.
We have drastically reduced inputs. We now are to the point where we've taken inputs out of the equation. We have no longer applied synthetic fertilizers. We don't apply any chemicals. We do nothing that is outside of trying to work with Mother Nature. Before we jumped into this organic leap of faith that we're on, we were at a massive reduction of inputs, 75% reduction of inputs. And we were still maintaining yield, if not increasing yield. So at that point in time, our ROI, which is your return on investment, was as high as it's ever been. Right now, we are on, I'm going to say $200 an acre of savings of inputs. And on a farm our size, that's a little over $1 million. That's serious money.
So in this case, we saw reservoirs increase and more available by using diverse nutrient systems. In this case, we probably see that we are using different forms of nutrients, not only just chemical fertilizer. And those diverse inputs are not only fertilizer, but nutrients coming from cover crops, compost, biochar, or crop residues, because and also maybe some slow release nutrients we can put in there.
I guess in a traditional sense, if I was going to farm this with mixed vegetables, I would have came in here, looked at the ground, rototilled it, and I could have done that and added my inputs. And what would have happened is I would have had to keep adding more inputs to get the yields I wanted. And then I would have started seeing disease, pest problems more and more, rain events that we get, my soil would have pounded and compacted, and I just would have continued to struggle, right? I would have just been continuing to be frustrated. But instead, we're going the other way. Like, we're continuing to regenerate, so things are actually getting easier. Like less weeds, less pests. We started at 1.5, 1.9% organic matter. We're now at a stable 3.5 to 5 to 6, depending where we're at. And now granted, that's because we have a really cheap carbon source that I've been able to get into the soils, and we've kept things covered and we haven't disturbed it. So it's a total system. I think that's what's making it work so far.
So in these systems, we have minimized tillage practices. So following the soil health principles, thus we can have more residue in the system. And another thing also we need to look at that once we are measuring nitrogen and phosphorus with those simple soil health tests, we actually measure only inorganic part of phosphorus by Bray or Malik or Olson method, and as well as the inorganic phosphorus we are measuring. But we need to look at the whole spectrum of phosphorus. Phosphorus is inorganic and organic form is there. Majority of it actually in organic form. So we need to measure the total phosphorus and same way to measure also total nitrogen. That's why we need to think about the soil health testing. So in this case, you can see this arrow is much narrower. It means we are using less chemical fertilizer and thus we have less leaching and running off and less gaseous removal of nitrogen. Plants, we are still using 4R strategy. So that's why we get the more efficient use of nutrients and plant can take up nutrients that way. And since we have a diverse inputs, so let's say we are also using compost or residue and other form of carbon amendment, that increase and also cover crops. So in this case, so these are all increasing the soil organic matter and also thrive soil habitats in there. In this case, so mineralization will be more, assimilation is going to be more because of biology in there. Biology is the one who actually mineralizing and assimilating all those nutrients in the soil. And phosphorus reservoir will increase because all those carbon amendment or residues has some phosphorus. It can also increase the reservoir of phosphorus. In this case, fixation will be less and phosphorus in the solution will be more. So let's talk a little bit about mineralization and immobilization. So mineralization is the process that by which microorganisms decompose organic nitrogen from manure, compost, residues, plant residues, and to form ammonium or nitrate. Ammonium also converted into nitrate with the bacteria, that is nitrosomonas bacteria. And the rate of mineralization and vary with soil temperature, moisture, and the amount of oxygen in the soil solution. And immobilization is the reverse of mineralization. So all living things require nitrogen. Therefore, microorganisms in the soil compete with crop for nitrogen. So in this case, you see the ammonium and nitrate with the help of microorganisms that it can form organic nitrogen. So this is also important to see once we are applying any form of residue, it has carbon and nitrogen ratio. Here you can see the 24 carbon to 1 is the ideal microbial diet. It goes above it, so the decomposition of the residue or anything actually slower down. And if it goes below, then decomposition is getting faster and faster. one example, you can see the rye straw carbon nitrogen ratio is 82:1. And when is the anthesis level, the rye cover has an carbon nitrogen ratio is 37:1. But when rye at vegetative stage is, carbon nitrogen ratio is 26:1, which is kind of close to microbial diet. So if you terminate at vegetative stage, so there is a possibility of microbial activities more, so nutrient also going to be released at this stage. Here, change in microbial activity in soluble nitrogen level and residual nitrogen ratio following the addition of either high, the upper figure, like, think about this figure has CN ratio is high, corn stover or mature small grain. So in the lower figure, it shows that, CN ratio is much lower. So it means, example is going to be like legumes, other forms. So the CN ratio is much lower. So as I say in previous slide, in this case, you see the nitrate depression period. So it takes a longer time for microbes to digest, nitrogens or decomposing materials compared to the below the figure. Here's a simple the small part of the process by, I think it's give you a basic idea of how life, death, and mineralizations occurs. This is all happening in the rhizosphere, because rhizosphere is the region of the soil in the vicinity of plant. So where the microbial activities is more, not only microbial, all soil habitat is more. Maybe it's 1,000 times more than the soil doesn't have the rhizosphere area. Why this is important? Because in the rhizosphere, plants actually provide food for the soil habitats. It is about 20% or more the carbon they capture from the air through the photosynthesis process goes to the soil to attract soil biology. So once the biology is working, so they also can get some nutrients from the soil for their growth. In this case, you can see bacteria with carbon and nitrogen ratio is 5:1, whereas in bacteria feeding in the right side, you see the bacteria feeding nematodes has carbon nitrogen ratio 10:1. So in this case, if a nematode actually consume a bacteria to get enough carbon for function and reproduction, what they do, they need only 1 part of nitrogen, because they get 2 bacteria, consume 2 bacteria, so it gives you 10 carbon, but 2 nitrogen, but it needs 1 nitrogen. So what it does, it secrete or excrete 1 part nitrogen to the soil solution. So the plant can have some, nutrients by the soil habitats activities like bacteria and nematodes you can see in here. So Nitrogen mineralization from crop residue and soil organic matter is highly soluble through the winter. Nitrate actually 100 times um, soluble than phosphorus, and it is 10 times more soluble than ammonium. So in nitrate leaching can be significant even without all nitrogen application. So, but what if you are planting a cereal crop? So do you want all your nitrogen tied up? Here is again nitrogen immobilization. You see the cover crop here in the left side has a carbon nitrogen ratio is 40 to 1. Whereas bacteria's carbon nitrogen ratio is 5 to 1. So what it does, so it consumes enough carbon from the rye for respiration and body structure. But it has a lot of carbon actually remaining here because it doesn't have enough nitrogen in here. So here you see the microbes using soil carbon to help cycle nitrogen, phosphorus, because as I said, plant takes, provide a lot of exudates or carbon into the soil. Here you see the rhizosphere, and exudates are, what is this? They are carbohydrate. They're also protein secreted by the roots that attracts bacteria, fungi, nematodes, protozoa, and all others, earthworm. So everything actually mineralizes nutrients for plant. This is the bacteria and fungi. They are kind of little fertilizer bags. If you grow them, if they give them a room to grow, so they even providing nutrients, and those nutrients is coming from the soil and all the residues out there. And nematode and protozoa also consume bacteria, and also they're providing nutrients to the plant. So one thing is see the phosphorus cycle. Phosphorus actually is non-renewable resources. These are coming from rock phosphate, and you probably see one of the island close to Nauru Island next to Australia, and it was full of rock phosphate. And there is no rock phosphate right now in there. So we all depends on the rock phosphate, and once it goes out, there is no phosphorus for us. But plant needs, human needs, everybody needs phosphorus. And you can see in here, mycorrhizal fungi in the right side, and in the left side, roots without mycorrhizal fungus. So, in the plant, about 85% of the plants actually making symbiotic relationship with mycorrhizal fungus. So what they do, they are increasing the depletion zone for the phosphorus to the plant, whereas also mycorrhiza is receiving carbohydrate from the plant. So this is the kind of mutual symbiotic relationship, between the plant and the fungus. So it's giving and take. You're giving nutrients, and not only just nutrient, also they're providing water and also stabilize the soil aggregates. And here's the water cycle. This is important for life on Earth. So, which includes soil biology and resulting crop productivity. So, if there is no water, there is no life. So, it is important to maintain optimum soil water level throughout critical period of plant growth. Soil waters affects nutrient management, both as a solution matrix for nutrients and for sustaining soil habitat responsible for cycling nutrients. In most fields, we can do a better job managing water and not just irrigation. We do not feel it is most important part of the water. But we do feel actually it's important part of the water cycle, and that can actually impact. So if you are doing a soil health practice, we have a more infiltration and there is a groundwater recharge possibility and less runoff. So the clean water is going out of the field to the water body. So most critical point of the water cycle is what is that? Aggregate stability. So if you have someone is doing a soil health practice, so it can increase the stability of the aggregate. Here also coming mycorrhizal fungus. So that is also improving and meshing all those aggregates to make it better soil aggregates. So soil aggregate instability, if there is no soil aggregate, it means compacted soil, and it also plug the pores, soil pores, and you see the ponding activities. You see this ponding in the land, many places in depressive area, and also runoff occurs, soil moving out of the field. Not only soil, all the chemicals and fertilizer, everything is applied also goes to the water body and causing the water problem. So soil aggregates, as I mentioned, improve infiltration and soil profile storage. Like, during the off season, if you keep the soil more in the soil profile, so the kind of is a saving account. So during the summer, you need less water. And also it can increase the groundwater recharge. And here's the relationship between soil bulk density and soil organic carbon. In the x-axis is the soil organic carbon. And once you have more soil organic carbon, the bulk density actually is going to be lower. Another, here you can see the carbon aggregates and infiltration. If you have a more soil organic carbon, infiltration is higher, and also aggregates will be higher. Here you can see the microbes actually can rescue, and this is a model of recruitment and activation of beneficial by the um, beneficial by the plant's uptake attack. Here you can see the red is the some of the in the left side is the invaders. They're pathogenic fungus or bacteria. They're coming to the root and should, and here also you can see, subsequently increase the secretion of microbial stimulant compound. So once you are increasing in the right side, include the microbial stimulant by secreting something by the plant, so that can recruit, activate plant beneficial microorganism, and beneficial microorganism can induce resistance. That you can see there also the green arrow directly or produce pathogen inhibitory compounds. So they also protect them by secreting some chemicals that attract beneficial and protect from the pathogenic organisms. So pest management, this is another area we need to discuss here. Here you see the plant benefits from microbes. Here you see the lower down here the suppressive soil, and in the axis is day after beginning of incubation. If you are incubating the suppressive soil, that actually becoming the conducive soil. You probably know what is suppressive soil and conducive soil. The conducive soil is that once people start fumigating or somehow try to remove all the biology from the soil. So what happened actually? That soil became more prone to pathogens. But if you keep the soil with the biology, ecology of all the soil habitats, so there's a good pathogen, a good bacteria and fungi, and pathogenic bacteria and fungi. So there is a interaction between them and causing suppressive soil. So there is a balance, check and balance. But if it is no balance in there because of fumigation, here you can see that when your autoclave, the soil of suppressive soil is turning into conducive soil.
As I'm thinking about how to manage my pests and get more beneficials, I want to put beneficial habitat as close to my cash crops as I can. So here's some peas, got some carrots over there, and a lot of the pests, there's a lot of pests, and I have to somehow arm my annual crops against those pests by giving them the beneficials a place to go. So what I decided on a practical level is just to sacrifice one bed. I have 100-foot beds here on the farm, and give it a permanent space of plants that are going to be flowering at different times. They're going to be different heights so that like a praying mantis case can come in and lay. I've noticed around here, praying mantis always do about this high. I don't know why it is, but that means if I only have short grass prairie or small habitat, I won't get praying mantis, which are like the lion of the predator world.
The idea is that, if you try to keep the soil really in good condition, then you have to allow the both biology to thrive or the soil habitat to thrive. So in this case, soil health principle is the one actually can bring suppressive soil. So it can increase the beneficial organism in there. Therefore, you know, producer can use less chemicals to control the pathogenic fungus or bacteria or any disease or pest they have.
Our corn is just as green as everybody else's, but we don't use near as many chemicals as we were before. With cover crops, to keep the weeds down, we saved ourselves $10 an acre in herbicides, and our cover crops expense was $5.
Covers and weed management. So weed management is an issue, and is hard to control weed. So it has a different way to control it, and one of them is to put the mulch or cover crops. So another thing is also possible that we can put a different strategy to control weed. So one of them would be like a row crop spacing. So one thing is to say here, one of the things is that after microenvironment during the weed seed germinations. So what is that? If weed seed receive a little bit of sunlight, so seed can germinate if the climate is favorable, like moisture, everything is there. But if you can keep some residue, mulch, or any other carbon amendment, so the weed seed cannot receive that sun light, so that they germinate less. And other things also true that some of the plant can produce chemicals that call allelopathic effects, and allelopathic effects can occur from what you call from cover crops as well. Like one of the experiment has done here in California shows that once we are using like a Sudan grass or the sorghum Sudan grass, and it can also produce allelopathic effects. And allelopathic effects actually affects against weed, but it can also affect in the subsequent cash crops. Once experiment has done here in UC Davis, they found that after putting a Sudan grass and subsequent crop of tomato, lettuce, broccoli from transplants shows symptoms of phytotoxicity, including necrosis, stunting, color changes. About 50 to 70% of transplant mortality in all three species. So in this case, yield also reduced. So you need to also think about both sides, putting some kind of cover crops that may affect the subsequent crops growth. So, but other technology you can use for weed control, say for example, row crop, like spacing, like corn growing like 30 inches row. If you can grow 50 inches, 15 inches row, the weed density is not going to be an problems. Or maybe the intercropping or some others form of, planting covers may reduce the weed population. Weed, another area we need to think about that is the other technologies such as, the critical time of weed control. Is it when is the time to use a herbicide? Like for examples, you can develop stage of corn. Like critical period of weed control is up to 10 leaf stage for corn. Like but if you are applying herbicide or after like 10 leaf stage, then there is not necessary to put any herbicide in there because actually plants is outcompete with the weeds. There are some other technology they use, like innovative technologies such as GPS or drone to see, where the weed population is there, or scouting even, because the weed maybe is not growing everywhere uniformly. Some places is really high in weed population, some other places is low in weed population. So in this case, scouting to apply spot application of herbicide to control weeds. And these are the way how to control weed. You see the one of this example is here. You can see the cover crop in wheat stubbles before grain sorghum. But once you have a more biomass in the cover crops, and it reduced the Palmer amaranthus biomass, because this is one of the, I think, herbicide resistance weed. I think throughout the world and the states, we have about 24 herbicide resistance weed, and it's growing. So it is important to think about how to control weed by using 4 soil health principles. I think you guys have any questions?
Have any questions? We appreciate it, Kabir. Thanks for presenting today.